1. An AC circuit with only an inductor. An AC circuit with only an inductor. The impedance Z appropriate to this situation is shown by point A in the complex plane. Z is equal to J omega L. The angle made by OA with the real axis is pi upon 2. Further, modulus OA is equal to omega L is equal to modulus Z. So the equation can be written as I is equal to Vm into cos omega t minus delta upon modulus Z. I is equal to Vm into cos omega t minus pi upon 2 upon omega L. We note here that in a circuit having only an inductor, the current lags behind the voltage by a phase equal to pi upon 2. 2. AC circuit having only a capacitor. AC circuit having only a capacitor. The impedance Z appropriate to this situation is shown by point A in the complex plane. Now, Z is equal to minus J upon omega C. And modulus Z is equal to 1 upon omega C. Position of Z in the complex plane is as shown in figure. Here, delta is equal to minus pi upon 2. Hence, the current and the voltage are now related as I is equal to Vm into cos omega t minus delta upon modulus Z. I is equal to Vm cos omega t plus pi upon 2 upon 1 upon omega C. Thus, in an AC circuit having only a capacitive reactance, the current leads the voltage in phase by pi upon 2. AC circuit having R and L in series. AC circuit having R and L in series. For such a circuit, Z is equal to R plus J omega L. Modulus Z is equal to square root of R square plus omega square into L square. In figure, Z is shown by OA in the complex plane. It can readily be seen that delta is equal to tan raised to minus 1 omega L upon R. I is equal to Vm into cos omega t minus delta upon square root of R square plus omega square L square. The current lags behind the voltage in phase by an amount delta as given by the equation delta is equal to 10 raised to minus 1 omega L upon R. 4. AC circuit with R and C in series. AC circuit with R and C in series. In this case, Z is equal to R minus J upon omega C. Therefore, modulus Z is equal to square root R square plus 1 upon omega square C square. Figure shows this Z in the complex plane. Note that delta is negative in this case and is given by delta is equal to 10 raised to minus 1 upon omega C R. I is equal to Vm cos omega t plus delta upon square root of R square plus 1 upon omega square C square. Current will now be ahead of the voltage in the phase by a value delta. AC circuit with L and C in series. The impedance Z appropriate to this situation, now Z is equal to J omega L minus J upon omega C. Modulus Z is equal to omega L minus 1 upon omega C. If we take omega L is greater than 1 upon omega C, Z will be shown in figure by OG. In this situation, delta is equal to pi upon 2. Therefore, if in an AC circuit with only L and C in series, if omega L is greater than 1 upon omega C, the current lags behind the voltage by pi by 2 in phase. AC circuit with L and C in parallel and R in series. Applying the rule of parallel connections to L and C, we have 1 upon Z1 is equal to 1 upon ZC plus 1 upon ZL. But ZC is equal to minus J upon omega C. ZL is equal to J omega L. Is equal to 1 upon minus J upon omega C plus 1 upon J omega L. That is equal to J into omega C minus 1 upon omega L. Therefore, Z1 is equal to 1 upon J omega C minus 1 upon omega L is equal to minus J upon omega C minus 1 upon omega L. Now Z1 and R are in series connection. Therefore, Z is equal to Z1 plus R is equal to R minus J upon omega C minus 1 upon omega L. Modulus Z is equal to square root of R square plus 1 upon omega C minus 1 upon omega L whole square. Expression for the current is obtained by using the above value for summation Z in the equation. Thus, I is equal to Vm cos omega t plus delta upon square root R square plus 1 upon omega C minus 1 upon omega L whole square. If we take omega C greater than 1 upon omega L, then Z will be represented in the complex plane as shown. Delta is given as tan delta is equal to BA upon OB is equal to 1 upon omega C minus 1 upon omega L upon R. That is equal to 1 upon R into omega C minus 1 upon omega L.